Hi, and welcome to part 3 of the SD Fabric tutorial. In this session, we're going to talk about the P4-based mobile user plane function, or P4UPF. So we're going to start by providing an overview of the P4UPF architecture and some details of the pipeline design. Then we will do an hands-on exercise where you can learn how to configure P4UPF, generate some test traffic, and finally observe switches performing GTPU tunnel termination. Okay, let's get started. So a UPF is essentially a specialized router that it's used in mobile core networks to process all user traffic. SD Fabric today provides two UPF implementations, a switch-based one and a CPU-based one. The switch-based UPF is called P4UPF because we use P4 to define the UPF packet processing pipeline. The CPU-based UPF is called BESS UPF, where BESS stands for Berkeley Extensible Software Switch, which is a framework for packet processing based on DPDK. In this session, we're going to focus only on P4UPF. So before getting to the nuts and bolts of P4UPF, let me give you a quick overview. First of all, you might be asking why implementing a switch-based UPF? Well, there are a few reasons. So first of all, P4UPF allows us to free up CPU resources, resources that can be instead used by edge applications, since now the UPF data path it's fully offloaded to switches. Second, P4UPF allows us to meet the performance requirements for Industry 4.0 use cases, so such as ultra low latency and jitter and very high throughput. P4UPF is not necessarily a full implementation of the 3GPP standard for UPF. Instead, it focuses mostly on those functions that are required for enterprise and IoT use cases. So the main functions provided today by P4UPF are obviously GTPU tunnel termination, including the necessary extensions to the GTPU header for 5G, such as QoS flow information. It also provides support for application filtering, slicing in QoS, usage reporting, as well as idle mode buffering. Finally, by running the UPF function as part of the switch pipeline that also supports INT, we are able to combine the two. So the UPF INT integration today allows us to essentially do a validation of service level agreements. So we can take a look at flows inside the GTPU tunnels for things like latency, congestion, or drops. An important design concept of P4UPF is the fact that we realize a so-called distributed UPF data path. So because SD Fabric supports multiple topologies from a single top of rack switch to a paired top of racks to a full leaf spine for multi-rack deployments, what we do here is we program all leaf switches with the same UPF rules that are used to do GTPU tunnel termination, as well as classifications for things like application filtering and QoS. So the main benefit for realizing a distributed data path are the following. First of all, it allows us to achieve minimum latency. So GTPU tunnels are terminated at the ingress leaf switch without having to detour packets through additional devices. So as soon as the tunnel is terminated, we can route packets to the next hop that could be an edge application running on the servers. Second, it enables fast failover. So when using paired top of racks, if one switch fails, the other one can immediately take over since it's already programmed with the same rules. Finally, it enables a fabric-wide quality of service. So because we do classification at the ingress of the fabric, and because we use a custom packet marking, we are able to carry the QoS information across the fabric and enforce things like scheduling priority at every op. Next, I want to provide a bit more details about our control plane architecture and how we can integrate with a standard 3GPP mobile core. As you know, we use switches running Stratum controlled by ONOS using P4 runtime and GNMI. On top of ONOS, we have a number of applications. You already learned about the trellis control apps to do things like basic routing, ECMP, and PLS. And here we learn about a new app called UP4. So UP4 provides what we call a one big UPF abstraction. So remember, because we use this distributed data path where multiple switches can actually perform the UPF function, we want to abstract this complexity to the mobile core control plane. And that's exactly the purpose of the UP4 application. The integration with the actual mobile core control plane, it's done through a component called PFCP agent. So PFCP is a standard 3GPP interface, and what happens here is that the UP4 app abstracts the underlying fabric topology as one virtual P4-based device programmed with a P4 program called virtual UPF.P4. So the PFCP agent believes is controlling one device, while internally the UP4 application programs multiple devices, multiple lift switches. And this allows us to scale the fabric topology independently of the mobile core control plane. So each time we need to add a new switch or remove a switch, we can do so without modifying the mobile core control plane. So what is exactly the role of the UP4 application? To explain that, it's important to highlight that in this architecture, we have two P4 programs. The first one is fabric.p4, which is what we compile and run on the switches. This P4 program is optimized for Tofino and defines tables for a number of functions, from routing to UPF functions. The second P4 program is virtual UPF.p4. This program defines only UPF tables, and it's not optimized for any hardware target. But most importantly, this P4 program doesn't run on any switch. Instead, it's only used by the UP4 application to define the content of the P4 runtime messages exchanged with PFCP agent. In other words, we use P4 mostly as an API data model. So the role of the UP4 app is that of translating P4 runtime entries from virtual UPF.P4 to fabric.P4, making sure to program all lift switches to realize the distributed data path. So about PFCP agent, you might be wondering why implementing the PFCP protocol as a separate component. Well, the reason is simple. PFCP is a complex protocol, and we'd rather implement it once and use it many times with different data paths. So remember, P4UPF is one possible implementation of a UPF. We also have a DPDK-based UPF data path, that's best UPF, and there can be other data paths. So the idea is to implement the complex PFCP protocol once and reuse it many times. Support for different data paths is made possible through an extensible southbound where we can have multiple plugins. So the plugins supported today are the UP4 plugin for P4UPF, the best plugin for best UPF, and if you decide to implement a new UPF, then you can reuse PFCP agent by providing a new plugin. Okay, now I want to spend some time talking about the P4 pipeline design of our UPF. So PFCP defines a very flexible match action abstraction that can match on a lot of headers and perform all sorts of different actions for QoS, GDPU and cap-decap, etc. The problem with such a very flexible abstraction is that it's very hard to implement in hardware without knowing exactly which kind of rules will be provided by the mobile core control plane. Instead of implementing the full capabilities described by PFCP, virtual UPF.P4 defines a simpler pipeline that formalizes a subset of the PFCP capabilities that make sense in enterprise use cases. The role of the UP4 plugin in PFCP agent is that of validating and decomposing the PFCP entities into one or more P4 runtime table entries for virtual UPF.P4. So let's take a look at the pipeline. So there are mainly 4 tables here to identify the UPF logical interface and the traffic direction, so whether it's uplink or downlink. The sessions table, it's used to identify the UE by looking at the GDP tunnel identifier, so the TID, or the UE IP address in the case of downlink traffic. The applications table instead implement wildcard match on the inner headers, specifically the inner IP prefix and port range, and that's used to identify the application. These 2 tables write 2 metadata, the application ID and the session ID. So the role of the termination table is that of matching on session ID and app ID to decide whether to drop packet in case we're doing so-called application filtering. If a packet is not dropped, then the termination table is the one setting the necessary metadata to do GTPU encapsulation and decapsulation. So we start from the logical representation of the P4 pipeline for the UPF. Now I want to go to the bottom, to the switches. But before doing that, it's important to do a quick overview of fabric.P4, which is the P4 program running on the switches. So the design of fabric.p4, it's essentially driven by the control plane. So in ONOS, we have the trellis control applications that use an API that is called Flow Objective. This is a Java API that abstracts a three-stage logical pipeline. These three stages are filtering, forwarding, and next. So a filtering objective, it's used to do VLAN-based port admission. A forwarding objective, it's used to essentially populate the forwarding information base. So forwarding objectives are those used to represent things like bridging entries, routing entries, MPLS, etc. Finally, next objectives are used to specify the actual forwarding action. So whether we need to rewrite headers, push or pop, headers like VLAN, MPLS, how to do ECMP, etc. The design of fabric.p4, it's based on what is almost a one-to-one mapping between the Flow Objective API and the corresponding P4 table. So if you look at fabric.p4 today, you will see tables essentially formalizing a filtering objective, forwarding objective, as well as next objective. The integration of the UPF with fabric.p4 is done by adding two sets of tables to the pipeline. We have UPF ingress and UPF egress. UPF ingress essentially provides tables very similar to virtual UPF.p4, but optimized for Tofino. The UPF ingress tables are placed before the forwarding stage, and that's because we want to do routing on the modified IP header. So if we do GTPU and CAP, then we want to route on the outer IPv4 destination address, which is the base station address. Finally, the UPF egress stage, it's used to realize things like egress counters for usage reporting and other function that makes more sense to realize at the egress pipe. Let's do a quick summary. So it's important to remember that P4UPF, it's realized using a distributed data path where multiple switches, leaf switches, are used to perform the UPF functions such as GTPU tunnel termination. Second, integration with the 5G mobile core is realized by two components. We have PFCP agent that implements the actual PFCP protocol. This component is reusable across multiple UPF implementations by using a southbound plugin mechanism, where UP4 is one possible plugin. UP4 is a ONOS application that provides a one big UPF abstraction, where the underlying topology, whether it's a leaf spine or a single switch, is abstracted as one virtual P4 runtime device to PFCP agent. Finally, remember that we have two P4 programs. One is virtual UPF.p4. This program represents a logical pipeline that doesn't run on any switch, and it's essentially used as an API data model for UP4, which implements a P4 runtime server. The second P4 program is fabric.p4, which instead is the one running on Tofino. There are a few things we didn't talk about. We didn't talk about how we do idle mode buffering, which is an important feature of UPF. We didn't talk about slicing in QoS and the INT integration. For some of these topics, we plan to make available dedicated tutorial sessions in the near future. If you want to learn more, you can check out our official documentation website or a paper presented at SOSR 2021 describing the architecture of our P4-based UPF. All right, let's move to the hands-on part. In exercise 2 of this tutorial, we're going to use the same leaf spine topology of the previous exercise. In this case, we're going to focus on only two hosts. We have a emulated base station, or GNOT-B in 5G terminology, and an application host. In the exercise, we're going to generate downlink traffic from the application host with IP address 172.16.4.1 to the UE attached to the base station, where the UE has IP address 192.168.0.1. We will program the switches to perform the UPF function. So in this case, we want to observe leaf2 performing GTPU encapsulation. So the output of leaf2 and the packet is actually received by the base station should be a packet with two IP headers. The outer one should have destination IP address the GNOT-B. There are a few steps required to configure P4UPF. First, we need to provide a netcfg JSON just for the UP4 application that specify which switches make up for the UPF distributed data path, in this case, leaf1 and leaf2. Second, we need to provide a piece of configuration, which is another JSON file, to PFCP agent. Here it's where we specify things like the UE subnet what is the IP address of the UPF. This is also called the N3 interface IP address in 5G terminology, and also what is the address of the P4 runtime server running on UP4. And with these two steps, we effectively have an operational UPF. So the last thing to do is to set up the necessary tunnels for UEs. To do this, we're going to use a tool called PFCP SIM to perform operations like PFCP association, as well as a session establishment, modification, and deletion. In the tutorial, instead of bringing up a full-fledged 5G mobile core control plane, we use a simpler tool called PFCP SIM that it's used to emulate what is the 5G SMF component. This tool is made of two different parts. There is a PFCP SIM container that is the one responsible for the PFCP communication with the UPF, as well as maintaining some session state. To be able to set up then the necessary UE rules, we use a CLI interface provided by a tool called PFCP Cattle that we're going to use to perform association requests, as well as create and modify UE sessions. Finally, a quick recap of the environment. We'll learn about this in the previous exercise. The important thing to remember here is that for what it concerns P4 UPF, remember that UP4 is an application running on top of ONOS, and so this is part of the SD Fabric Docker container, while PFCP agent and PFCP SIM ran as a separate containers. And we will see how to start these containers as part of the exercise. So here are the steps of the exercise. We're going to start by opening up and modify the configuration files for PFCP agent and UP4. We're going to start the PFCP agent container, and then we're going to use PFCP Cattle to set up a UE session. Finally, we're going to use some Python scripts to generate and sniff traffic and observe whether switches are performing GTPO encapsulation as expected. If you want to work on the exercise on your own, remember that instructions are available on our GitHub repo. Now I want to quickly show you a preview of the exercise. Here I have the environment running from the previous one, including the ONOS log. The first thing to do is to look at the configuration file. So we start with the config file for the UP4 application. Here we notice two things. The first one is that we define a new interface. On leaf 1, this is the interface connecting to the G node B, so the emulated base station, and we assign IP address 172.61.1.254. The second piece is the configuration for the UP4 app, where it's important to note how we configure two devices, leaf 1 and leaf 2, to be part of our distributed UPF data path. Second, we take a look at the config file for PFCP agent. And we can see how we specify three things. First of all, the UE subnet 192.168/16. Then the IP address and port of the P4 runtime server for the UP4 app. And finally, the access IP. This is also called the N3 interface address. Note how we're using the same switch interface IP address configured in the netcfg file. So now we can push the netcfg for UP4, and we can see that something is happening in the ONOS log. Now we can finally start the remaining container. So we do make start UPF, and this is going to start two things, PFCP agent and PFCP SIM. In the ONOS log, we notice that there is a new connection on the UP4 P4 runtime server, and that PFCP agent already installed two rules. These are source interface rule to classify traffic either coming from the core interface or the access interface. Now it's time to use PFCP Cattle. We start by configuring PFCP SIM. So we use the command PFCP Cattle service configure. What we're doing here is we're telling PFCP Cattle that we want PFCP SIM to connect to this instance of PFCP agent and to use the following N3 address. So this is the same access IP address in the PFCP agent config file. Run the command and we can see the command is successful. Now we start a so-called PFCP association request between PFCP SIM and the UPF, and we can see that it is also successful. Then we run a
pfcp session creation command. This is going to install tunnels for one UE using an IP address from the provided pool and the following GNetB address. So we run the command and we see that we have one session installed. And looking at the ONOS log, we notice that PFCP agent actually installed a number of entries. So we can see the session uplink entries, we can see a termination uplink entry for the UE IP address .0.1 and an application ID. 0 means default in this case. The PFCP specification requires to also issue a modify command to essentially enable the downlink traffic. So as we run this command, we notice how before the termination downlink entry had a drop action. And after the modify command, we see how this is being changed to forward. So let's see if this works by running some traffic. So we start by running a script on the GNetB side to actually listen for GTP packets. This script will print a line for each packet received. Then we start another script to send UDP packets from H4 to the IP address of the UE, so 192.168.0.1. We run this command and we see that we are indeed receiving traffic on the GNetB side. If we look closely, we notice that this packet has two IP headers. The outer one is from the UPF IP address to the base station IP address. We can see that the GTP encapsulation is present. And we can see that the inner IP address shows how we're sending traffic from H4 to the UE IP address. That's all for the exercise overview. If you want to work on the exercise on your own, make sure to check out the GitHub repo. That's the end of today's tutorial on SD Fabric. We plan to publish more sessions in the near future, so make sure to subscribe to our GitHub repo to be informed about new sessions. Thanks for watching.